Hello, and welcome to Probability Part 2. In this video, we'll discuss conditional probability, as well as tests for independence. Conditional probability is the probability of an event, say A, based on another event, B, having already occurred. We write the probability of event A given B as P, parenthesis A, vertical line B. We read it probability of event A given B. For example, say I work outside at a golf course. Let W be the event I go to work today, and let T be the event there will be thunderstorms today. Perhaps the probability of W is 0.8, but the probability of W given T might be 0.1. What we're saying essentially is that the probability that I go to work in general on all days is 0.8 or 80%. However, on days there are thunderstorms, the probability that I go to work drops to 0.1 or 10%. The probability of A given B is equal to the probability of A intersection B divided by the probability of B, or the probability of A and B divided by the probability of B. They're in essence the same formula. Given the two-way frequency table below, what's the probability a family has a cat given they have a dog? Here's the information you can see. Here are the people that have dogs. Here are the families that do not have dogs. Going across the top row are the families that have cats. Going across the second row are families that do not have cats. Since we want the probability that a family has a cat given that they have a dog, we're only going to consider the dog people. How many of those have cats? Well, 110 do, out of the total of 640 dog families. Therefore, the probability of having a cat given you have a dog is 110 out of 640, or about 17%. Be careful not to switch them around because conditional probability is not commutative. The probability of having a dog given you have a cat is twice as likely. It's 110 out of 320 because now we'd be looking across the top row. Of all the cat people, which there are 320, 110 of them have a dog, 34%. Here's a new example. Say the probability of A is 0.7, the probability of B is 0.4, and the probability of A union B is 0.9. Again, that could be A or B. It's 0.9. Determine the probability of A given B. Since the probability of A given B is equal to the probability of A intersection B, or A and B, divided by the probability of B, but we don't know the probability of A and B, our first step is to determine the probability of A and B. We reach back to the addition rule from the first video lesson. The probability of A or B is the probability of A plus the probability of B minus the probability of A and B. Well, substituting in the values from the given, we'd have 0.9 equals 0.7 plus 0.4 minus the probability of A and B. And if we solve that for the probability of A and B, we get that to be 0.2. So now we can conclude that the probability of A given B is 0.2 divided by 0.4, or 0.5, which is 50%. Next, we're going to talk about independence in independent events and tests for independence. Let there be two events, say event A and event B. The events are said to be independent if the probability of event A does not change whether event B happens or not, hence independent. Two events are said to be independent if the probability of an event is unaffected by the outcome of the other event. That's just another way of saying what we said the first time. Mathematically, though, we could look at it this way. Events A and B are independent if the probability of A given B is equal to the probability of A in general out of the entire population. Or events A and B are independent if the probability of A and B is equal to the probability of A times the probability of B. We're going to look at this second one and see why that's true. So, the given, the probability of A given B is equal to the probability of A and B divided by the probability of B. That was from our definition of conditional probability. We'll call that equation 1. If A and B are independent, then the probability of A given B is equal to the probability of A. That's by definition. That was from the previous slide. We'll call that line 2. Therefore, the probability of A and B divided by the probability of B would have to equal the probability of A. Now, where did this come from? It's by substitution. I'm replacing the probability of A given B in line 2 with the result in line 1. Finally, if I multiply each side of equation 3 by the probability of B, we end up with probability of A given B is equal to the probability of A times the probability of B. And that's the end of our proof. Quod erat demonstrandum. If you look up here, this result in line 4 was completely dependent upon line 2, that if A and B are independent, then the probability of A given B is probability of A. If they're not independent, then that's not true. And so then lines 3 and 4 would no longer be true. So this is only true if A and B are independent events. Here's an example. In the classic dice game Yahtzee, a large straight is scored when a player has all 5 dice in consecutive order. There are only 2 possible combinations to score a large straight. Either you have a 1, 2, 3, 4, 5 on your 5 dice, or you have 2, 3, 4, 5, 6. Let's say a player has 4 of their 5 dice in consecutive order after the second roll of their 3 possible rolls. Is the probability of scoring a large straight on a final roll of a player's turn independent of which 4 consecutive numbers a player has? Well, let's take a look. There are 3 possible sequences of 4 consecutive numbers using regular dice. They are as follows. Let's set A be 1, 2, 3, 4, or B if we start with 2, 2, 3, 4, 5, and C could be if we started with a 3, 3, 4, 5, 6. To have the best odds of getting a large straight, a player would leave the 4 dice as shown and only roll the 5th die not yet in the sequence. So in the scenario with set A leading into the final roll, only a 5 will complete the sequence. That would give the large straight 1, 2, 3, 4, 5. Hence, a player would have a 1 out of 6 chance of scoring a large straight. In scenario with set C leading into the final roll, only a 2 will complete the sequence, putting it at the start of this consecutive list, 2, 3, 4, 5, 6. Hence, a player again has a 1/6 chance of scoring a large straight. However, in the scenario with set B leading into the final roll, either a 1 would complete the large straight, 1, 2, 3, 4, 5, or a 6, 2, 3, 4, 5, 6. So B leads to 2 opportunities on our last roll to complete the large straight. Hence, a player has a 2 out of 6 or a 1/3 chance of scoring a large straight. Therefore, the probability of scoring a large straight is impacted by which particular 4 numbers the dice form a sequence of. So therefore, the events are not independent. Here's another example. Say the probability it will rain on any day in April where I live is 0.3. The probability I will eat a peanut butter and jelly sandwich for lunch is 0.5. And the probability that I will both not eat a peanut butter and jelly sandwich for lunch and that it will not rain that day is 0.35. Show mathematically, in at least 2 different ways, that the probability it will rain in April where I live and the probability of me eating a peanut butter and jelly sandwich for lunch are independent events. Create a 2-way frequency table and a Venn diagram of the possibilities for this scenario. We'll let S stand for the sandwich, I eat peanut butter and jelly. We'll let R stand for rain, that it will rain. Since the probability of not S and not R equals 0.35 from right here, then either if I eat the sandwich or if it rains or both is the complement of this set, which would be 1 minus 0.35 or 0.65. By the addition rule, the probability of S or R equals the probability of S plus the probability of R minus the probability of S and R. Substituting in our values from our given and what we found here in the second line, and solving for the probability of S and R, we get the probability of S and R to equal 0.15. Now, I could have also done it by first creating the two-way frequency table. What I would have are all the black numbers. So the probability of rain, we're told, is 0.3. The probability of eating a peanut butter and jelly sandwich is 0.5. The probability of neither is the intersection of this column with this row, 0.35. And in the lower right corner is always 1 because it needs to be the total of all possibilities. With those four numbers in place, the black numbers, we'd then be able to figure out the two red numbers. 0.5 plus 0.5 is 1, and 0.3 plus 0.7 is 1. Once you'd have the two red numbers, then you'd be able to find the two blue numbers. 0.15 plus 0.35 is 0.5, and 0.35 plus 0.35 is 0.7. Once the blue numbers are in place, we'd then be able to figure out the probability of rain and eating the peanut butter and jelly sandwich, because 0.15 plus 0.15 is 0.3. Furthermore, 0.15 plus 0.35 is 0.5. Here's the same information displayed in a Venn diagram. The overlap between the two circles is 0.15. That's the probability of both eating a peanut butter and jelly sandwich and it raining. The 0.35 outside both circles is the probability that it will not rain and that I will not eat a peanut butter and jelly sandwich. The events R and S are independent if the probability of S given R equals the probability of S. We're saying the probability for S doesn't change. Since the probability of S given R is the probability of S and R divided by the probability of R, S and R is the 0.15 here, or the 0.15 here that's highlighted in yellow, divided by the probability of R, which is this entire circle, which is 0.3. I have to add those two numbers together. Or it's the total underneath the probability of rain in the first column of my two-way frequency table. That turns out to be 0.5. And it was also given that the probability of S was 0.5, so therefore they're equal. The events would then be independent. 2. The events R and S are independent if the probability of R given S equals the probability of R. Similarly to what we had done the first time, the probability of R and S is still the overlap, 0.15, but this time it's out of the probability of S, which is this entire circle. Add 0.35 and 0.15 and you get 0.5. Or you could take it from the total of the probability S row, 0.5. 0.15 divided by 0.5 is 0.3. And it was given that the probability of rain is 0.3. So since they're equal, the events are independent. Third and final way. To show that the events are independent, we could use the second formula, that the probability of S and R equals the probability of R times the probability of S. Since the probability of S and R, once again, is that overlap of 0.15, we're highlighted here in yellow, 0.15. But we already know the probability of R is 0.3 and the probability of S is 0.5, and when I multiply those together, I get 0.15, which is the same result as the probability of S and R. Since they're equal, the events, once again, are proven independent. I think this third way was probably the easiest way. Final example. The data below shows the probability per year of US drivers having an accident, or not, based upon two different age groups. So we can see going across the top rows the probability of 16 and 17-year-olds being in an accident versus not being in an accident. That's out of the entire population. And they make up a small total, relatively speaking, because they really don't represent too many drivers driving too many miles. Now the probability of not being 16 or 17 years old would be 18 on up. Could be 18 up to somebody well into their 90s who's still driving. The probability they have an accident, because they're a much larger group, is higher than the probability of a 16 or 17-year-old being in an accident. However, they make up by far the largest group of the probability of not being in an accident. So drivers 18 on up make up over 97% of the entire driving population. 16 and 17-year-olds make up less than 3%, but together they equal 100% or 1. Of all drivers, the probability of having an accident is here, and not having an accident is here, about 99.5%. Let A stand for the event having an accident, and let S stand for the event of being 16 or 17 years old. What percent of all drivers are predicted to have an accident this year? Of all drivers, right here, 0.005270. And if I multiply by 100, I get 0.527%. So about half of 1%. What is the probability of having an accident this year given the driver is 16 to 17 years old? Given that the driver is 16 to 17 years old, we're only looking at the top row. It's like, forget about the rest of the data in this table. 0.000103 is the probability of having an accident out of all of the 16 to 17-year-old drivers, which is 0.028876. When I divide it out, I get 0.00357, or about. So what's interesting is you always hear how 16 and 17-year-olds aren't as good of drivers, but yet they're involved, relatively speaking, in fewer accidents. Even though the age group of 16 to 17-year-olds have the highest rate of accidents per mile driven for all age groups, they also represent an age group that generally doesn't drive nearly as many miles per year as the other age groups. Is the probability of having an accident independent of being in the age group of 16 to 17-year-olds? Now, since the probability of A given S, which is my answer to question 2, doesn't equal the probability of A, which is my answer to question 1, A and S are not independent events. So if 16 and 17-year-olds were putting on as many miles as mom or dad, then they would have far more accidents. But it's because they're driving so relatively few miles that they have so relatively few accidents, all in all. Anyways, once again, there it is. I'm Murray Wright. Thanks for watching.